Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, great to be back. It's always exciting to see where the field is going.
Yeah, though sometimes I think we're just spinning our wheels, but always good to chat about it.
Hoping for some breakthroughs today, maybe even a paradigm shift.
So, I was reading that new paper on integrating spiking neural networks with neuromorphic hardware, and it got me thinking, are we really tapping into the full potential of neuroscience when building AI? It seems like we're still heavily reliant on these backpropagation-based systems, which are, well, very far from how the brain actually works, right?
Well, I see your point, but backprop, for all its differences from biological learning, has been incredibly successful. I mean, look at the image recognition tasks, the natural language processing. These models are getting so good. We're talking about systems that can generate coherent text, translate languages in real time. It's kind of mind-blowing when you actually think about it.
Yeah, but good is relative, isn't it? They're really good at pattern matching. I'm not sure that actually demonstrates intelligence. We throw huge data sets at these things, and yeah, they learn correlations, but where's the understanding? The reasoning, the ability to apply that knowledge to novel situations. It just feels fundamentally different from how humans process information.
I agree. It's like we've built these incredibly powerful but very specialized tools. They're like savants, excelling in one particular domain but falling flat on their face when you ask them to do something even slightly different. We still haven't got that general purpose intelligence, the ability to flexibly adapt and learn from sparse data, which is what humans do, right?
Exactly. And that's why I think we need to look deeper into neuroscience. Things like hierarchical temporal memory, predictive coding, and yes, even spiking neural networks. These are all inspired by biological systems and offer different learning mechanisms, right? I mean, backpropagation is very good at minimizing error, but does that translate into true understanding? Or is it just a really good optimization algorithm?
Okay, I see the argument for incorporating more biological mechanisms, but I think it's also worth remembering how far we've come. I mean, deep learning, despite its lack of direct biological plausibility, has achieved feats that were considered science fiction just a decade ago. We've seen advancements in convolutional neural networks, recurrent neural networks, attention mechanisms, and transformers. Consider the advancements in generative models like diffusion models, which allow us to synthesize realistic imagery from nothing. These things weren't possible in the past, and that all builds on the backprop algorithm.
But isn't that just scaling up existing techniques, throwing more data and more compute at the problem? Sure, it gets better results, but it's not fundamentally moving towards intelligence. It's not really understanding the world. It's learning relationships in a large dimensional space. It's not true cognition. I think we need to move beyond connectionist approaches. We need to consider more neurosymbolic approaches.
I think both of you have valid points. I mean, the scaling up of deep learning has definitely yielded impressive results. But I'm with you. We're reaching a point of diminishing returns with this architecture. I suspect that a key element is missing, something to do with the representation of space and time. The way we currently encode the information is very static, it feels like. It's all about abstract feature vectors, not the actual structure of the world as it unfolds in time. Think about how a baby develops its understanding of objects through its interactions with the world. It's not about static images, but dynamic sequences of sensory and motor experiences.
Yes, exactly. And it's not just about the static representation of an object, but the relationship between the object, the environment, and the agent. The brain doesn't just process information in isolation, it's constantly integrating and updating its internal model of the world. Backprop doesn't provide this kind of dynamic processing. It doesn't allow for the kind of constant revision of beliefs based on new information. And that's where things like Bayesian inference and predictive coding, which are seen in the brain, come in.
Okay, so you're suggesting that we move away from a purely data-driven approach and start trying to integrate more biologically inspired mechanisms. I get that, but it's not always clear which biological mechanism is the right one to be inspired by. And sometimes our simplified models of biological systems lose key components of biological learning, or at least make a lot of assumptions. For example, take the spiking neural networks. Yes, they are closer to how neurons operate, but they're also quite computationally expensive. And it's difficult to achieve the same level of performance as a traditional artificial neural network. It may be we are still missing key components we aren't able to replicate currently.
But what if the key isn't just more biologically inspired neural networks, but incorporating more symbolic and structured reasoning? The brain doesn't just store correlations, it creates models, it reasons, it plans. We need to find ways to integrate the flexibility of connectionist networks with the structured reasoning of symbolic systems. Maybe some kind of neurosymbolic hybrid architecture that can combine the advantages of both.
And I think that's part of the spatiotemporal processing I was talking about earlier. The brain seems to be able to seamlessly translate between different representations. You see an object, you touch it, you hear it. You remember how it moved yesterday. All these are represented in different formats. The core algorithm should be able to understand the intrinsic relationships, regardless of coordinate representation. And I think it is this missing piece. Right now, we're kind of stuck in this coordinate system with these abstract feature vectors, but the core algorithm we use should be invariant to these changes. Think about the frame problem in AI, the inability for AI to update its model of the world efficiently. The current systems struggle because they can't translate the world in an efficient manner. It's a bit like brute force.
Yeah, it's not just about a single aha moment. It's about a continual refinement of that model. We could look at how the brain uses prediction errors to update its beliefs, or how it navigates a complex environment. These are things we can integrate into our machine learning algorithms. For example, predictive coding. The brain constantly predicts the input it's about to receive, and then updates its internal model based on the error between the prediction and the actual input. This is a super efficient way to learn. We see examples of it in sensory processing.
Right? I mean, the predictive models are fascinating. And yes, maybe incorporating more biologically plausible forms of feedback and error correction could lead to some interesting advancements in network training. But the backprop is a very efficient optimizer, and we've seen great results with it. I do wonder if the computational cost is worth the change. I mean, we're constantly pushing for more efficient networks. We see a lot of work on pruning and quantization to compress the networks and make them faster. And we've been seeing advancements like in federated learning, where the model doesn't need to have all the data on one machine. It can learn from multiple places without having the data on one machine. We're also seeing improvements in the algorithms to train the models like Adam and its variants. We're not quite at the stage of true AGI, but I think we are moving in the right direction with deep learning.
I think that these are all improvements, but I don't think these are breakthroughs. The core issue is that these deep learning networks learn relationships in a very large dimensional space, but they don't actually understand the relationships. They are more like sophisticated curve fitters than real reasoners. We need to give these networks the ability to represent symbols and rules, and also allow for reasoning using these symbols. We need something beyond just weighted connections and backpropagation. The brain is not just a big connectionist network. It also encodes knowledge through symbolic representation. Think about how you form a concept like cat. It's not just an activation pattern. It is linked to other symbols and concepts, and you can do reasoning about cats and their relations to other things. And that's where neurosymbolic AI comes in. We need hybrid systems that integrate the best of both worlds.
And that gets to the point of representation again. I mean, symbolic AI had its own issues with scaling and brittleness, but the idea of discrete symbols that can be manipulated and reasoned about is still powerful. It's about finding the right way to represent the information, not just raw data, but also its relationships in both time and space. And it goes beyond current deep learning and also classic symbolic AI. How do we get a model that can understand an object in multiple coordinate frames or time, and that also encodes it in a symbolic and learnable way?
And I think that's the key challenge, right? It's not just about building better deep learning models, but also incorporating the structural and temporal elements that we know exist in biological systems. The brain is not a static machine. It's a dynamic system that is constantly updating its internal model of the world. I mean, consider the hippocampus. It's constantly creating these spatial maps, which are not static but change over time. We can look at grid cells and place cells and try to implement these in machines. These are real biological structures. I think that we need to look at the hardware as well. Standard von Neumann architecture is not really designed to process these time-based spatiotemporal patterns, right? We need neuromorphic hardware that can better mirror how the brain actually processes information.
Yeah, I get the argument for neuromorphic hardware. And yes, the current von Neumann architectures are a bottleneck. But neuromorphic is still fairly new, and we still don't have a full understanding of all the intricacies of the brain. We've seen a lot of progress in the past few years with standard hardware, so why move away from it when we see so many improvements? I think we are on the right path with deep learning models, the advancements we have seen in the past few years with transformers. Convolutional networks, graph neural networks show that deep learning is a very powerful tool. And with more data and compute, we can get close to AGI.
I agree that deep learning is impressive, but it's like trying to build a car by throwing millions of parts together and letting an algorithm assemble them. You might get something that rolls, but it's unlikely to be a very good car. It doesn't understand the principles of engineering and mechanics. We need something that is designed, not just evolved. We need to move away from just scaling up neural networks and embrace more neurosymbolic AI. We need to find ways to get our networks to reason like humans by combining the best of both connectionist and symbolic AI.
Exactly. And I think part of that design involves understanding how the brain represents information in spatiotemporal contexts and how it shifts between these representations. This could include things like creating an internal coordinate system that's flexible and adaptable to changes in viewpoint and time. The current deep learning models are brittle and inflexible, and it's because they are basically mapping functions from point A to point B, but lack any understanding of the underlying geometry. And when you change the point of view or the time frame, it completely breaks. It's very brute force in nature.
So, I think the key takeaway here is that we need a more holistic approach. We need to combine deep learning with insights from neuroscience, cognitive science, and symbolic AI. We shouldn't just keep scaling up current techniques or thinking in the same old paradigms. We need to be exploring things like hierarchical temporal memory, predictive coding, spiking neural networks, and neurosymbolic approaches. And we need to start thinking about not just what the algorithm does, but how the information is represented and how it is processed, both spatially and temporally. It's not just about optimizing for accuracy, but actually understanding the underlying mechanisms that give rise to intelligence.
Yes, I agree that a more holistic approach is definitely beneficial. I'm not suggesting we abandon deep learning. It has been very successful and is a powerful tool. But we should combine it with more biologically plausible learning algorithms. Incorporating things like predictive coding into existing deep learning models could actually yield some interesting advancements. And we need to keep developing more efficient training methods. I still believe the scaling hypothesis is valid, but we need to address things like energy consumption of our networks. We also need to look at ways to make our systems more robust to adversarial attacks and to generalize better to data that is outside of their training distribution.
Yeah, and I think for my money, the future really lies in neurosymbolic AI. We need to combine the learning capabilities of neural networks with the reasoning capabilities of symbolic systems. We need to build systems that can understand cause and effect, that can reason about the world, and that can solve problems in novel situations. And that means moving beyond just connectionist approaches and embracing hybrid systems, and I don't think the scaling hypothesis applies. It's more like we need a new type of algorithm.
And I think that moving beyond connectionist approaches means looking at how information is represented not just in a static sense, but also dynamically in both time and space. It's about how our models transform information between different coordinate systems. That's the key, I think. I think that focusing on this idea of invariant transformation, this ability of translating knowledge between different coordinate systems, will lead to truly general AI. I think current deep learning architectures just aren't capable of capturing that. I think the future direction is figuring out the minimal algorithm that can perform this, not adding to the already bloated deep learning architecture.
So, where should future research be going? From my perspective, I'd like to see more work on combining neuromorphic hardware with more biologically plausible learning rules, focusing on things like hierarchical temporal memory, predictive coding, and spiking neural networks, and integrating these more dynamic learning mechanisms with existing deep learning models. I also think we need more work into understanding the neurobiological mechanisms of memory, learning, and attention, and how they relate to intelligence. We can learn so much from studying the biological mechanisms, and we need to use this to build better AI systems.
From my angle, I think we should be focusing on developing more efficient deep learning architectures that can run on less compute. We need to address the energy consumption problem of these systems. They are becoming too expensive to run. We also need to improve the robustness of deep learning models so that they are not easily fooled. We need more research into model interpretability and explainability so that we understand why our networks make the decisions they do. We can also integrate more biologically inspired learning algorithms into our existing deep learning models, like predictive coding and attention mechanisms. And I also think scaling is still important, that with more data and compute, we will get closer to true AGI.
I think we need a real shift towards investigating neurosymbolic architectures that can combine the flexibility of deep learning with the reasoning power of symbolic systems. We need to create algorithms that can reason about cause and effect and learn complex relationships. And I think we need to rethink our approach to learning. The brain isn't just a connectionist system, it encodes knowledge in multiple ways through symbols and rules, and we need to build AI that can do the same.
And from my viewpoint, I think we need to really focus on understanding how the brain represents information in a spatiotemporal manner. We need to focus on building AI systems that can understand objects not as static feature vectors, but as dynamic entities that exist in a coordinate system. This will mean designing algorithms that can translate information between different coordinate systems and that can reason about the world in a way that is invariant to the point of view or time. We need to look at what the minimal algorithm for achieving this invariant transformation actually is. And it's not the bloated neural networks we have currently.
Well, that's a lot of different research avenues to explore. I think we should leave it here. I'm looking forward to seeing what the future holds, and hopefully, we'll be having this conversation again soon with some exciting new breakthroughs.
Definitely, it's always good to have these discussions. I'm optimistic about the future, despite some of the challenges. I think we're on the cusp of some major advancements.
Yeah, well, I remain skeptical, but I'm always eager to see new ideas, and I am hopeful that we move in the right direction. Thanks for the chat.
Agreed, it's always a stimulating conversation. We're bound to make progress, hopefully in the directions we all laid out. Until next time.